And then exam 2 will cover lessons 11 through 18. And so to compensate for the fact that exam 2 will take place in this window, there will be no class on Monday, October 12th. Okay, so so quiz 5 opens up today, covers lessons 13 and 14. You have until tomorrow morning to do it. And then quiz 6, you have Wednesday of next week to Thursday of next week to complete quiz 6, covers lessons 15 and 16. Okay, so now let's take a look at this warm-up problem that I provided for you guys. So the premise is that we have v, h, and r are differentiable functions of time t, and we're asked to differentiate the equation below with respect to t. So, have you guys had a chance to be able to look at this warm-up yet, or would you guys like a second to take a look at it? Okay. Okay. So here's what we will do. So who just show of hands, who has an idea of what the solution to the warm-up should be? And so. Okay. Well, so what do you have then?
I have dv over dt equals 7 pi dh over dt plus 2r e to the r squared times dr over dt.
Exactly. Good. So times dr over dt. Good. Okay. Because so what happens is that if you differentiate this with respect to t, well, you have dv over d over dt of v. So in this case, you just have dv over dt. And then in this case, you have d over dt of 7 pi h plus d over dt of e to the r squared. Okay? So here what we have is that, in this case, we have the derivative of 7 pi h with respect to t. So in this case, as we established before, you would differentiate this part like you normally would with respect to h. So this would just be 7 pi. But then you ultimately have to multiply this with dh dt. So that's where we have 7 pi. So that's the differentiating this part with respect to h. And then dh dt. Okay. And then this part here, you differentiate this part with respect to r. So we have 2r e to the r squared. And then times that by dr dt. Okay. Because you're differentiating this with respect to time t. Okay. So this would be the answer that you get out of the warm-up. Okay. So any questions on that? So now that we have that, just a quick little warm-up for you guys to help us get us going with the related rate stuff. But before we get into part 2 of our related rates discussion, does anyone have any questions on the homework for part 1? Okay. So here's what we'll do. Okay, so lesson 16, let's talk about some more related rate stuff. So today we'll continue our discussion on related rates, but in this case we're going to focus on real-world applications involving right triangles and trigonometry. So here's where we're going to write some preliminary stuff, so let's go ahead and do that. Okay, so let's draw our triangle first. So we have a right triangle. So here's our good old right triangle. So what we're going to do is we're going to denote this part here by x. We're going to denote this by y, and this by z. And we're also going to have this angle theta here. Alright? So what I'm going to do is say, alright, so the thing is that for any of these problems, x, y, z, and theta can go in any direction or remain constant depending on what the problem is asking us to look at here. So we have x, y, z and theta can go in either direction. Or be constant depending on context. Okay. So we'll see more of that in a bit, but for now let's go ahead and sort of label some of these sides a bit more. So what we have here is that, so in this case what that says is that x can go in either this direction or this direction depending on the context, and that would correspond to the rates dx dt. Similarly, y can go up or down, so this would correspond to dy dt, and then z can increase or decrease, which would then be corresponded to dz over dt. dz over dt. Okay. And then when applicable, theta can also increase or decrease, and that will be corresponding to d theta over dt. Okay. Alright. Okay, so that gives us a basic idea of how we are going to be dealing with right triangles in this situation. So let's sort of take a look at that 5-step process that we talked about last time in the context of dealing with right triangle applications to related rates. So basically the only one that sort of we really need to focus on with respect to that is the first step, which identifies the needed formula. So with right triangle problems that we're going to deal with in this homework, if there are no angles involved at all in the problem, or it's not needed in any way, just go ahead and use the Pythagorean theorem. Otherwise, we need to wait until after step 3 to see which one we actually need. So to see what I mean by that, here is the list of step 1 formulas. Okay. Oops. Okay, yeah. So in this case, as I mentioned, one of them is the Pythagorean theorem. Pythagorean theorem, which of course states that we have x squared plus y squared equals z squared. Equals z squared. Then the next few are going to involve trig equations. So if you remember SOHCAHTOA, that's where these are going to come into play. So some useful ones that will help out are going to be sine theta, cosine theta, and tangent theta. So let's do a quick review of these. So if we apply SOHCAHTOA to each of these trigonometric functions, what would sine of theta be? Yep.
Opposite over hypotenuse.
Yep. Opposite over hypotenuse, so opposite over hypotenuse, so y over z. Okay. So do the same thing with cosine theta, we get someone else?
Adjacent over hypotenuse.
Yep. Adjacent over hypotenuse, so x over z. And then tangent of theta will be opposite over adjacent, so y over x. Okay. So here's a list of step 1 formulas that will be useful in the context of step 1 stuff. Okay. So one thing to note here is that if we focus on some problems involving the angle, so note, if x is part of the quote-unquote ground, and z is the line of sight to an object above and respectively below the ground. Theta is the angle of elevation if the line of sight is for an object above the ground, but if it's below, then it's the angle of depression. So, just one thing to keep in mind for that. So, any questions on that? Alright. Okay. So that's all I really wanted to say on stuff regarding step 1, but then step 2 through 5 are basically the exact same from last time. So identify which variables need to change or vary with time t and which are constant, and then plug any constant values into the formula if applicable. Determine what values and rates are given and which we need to find. Then take the derivative of both sides with respect to time t, and then plug in the values and solve for the desired quantity. Okay? So let's go ahead and take a look at that. So, example 1. So, is anyone still writing this stuff down? Okay. So, example 1. The premise is that a ladder, square root of 8 meters long, rests on horizontal ground and leans against a vertical wall. The foot of the ladder is then pulled away from the wall at a rate of 0.7 meters per second. How fast is the top sliding down the wall when the foot of the ladder is 2 meters from the wall? Okay? So, for this problem, let's go ahead and denote this part here by x, this by y, and this by z. So the ladder is z, the wall is y, and x is the ground. Okay? So the thing is that, well, we don't really have to deal with any angles in this problem, as you may have noticed. So the good news is that with step 1, so no angles, implies you have to use x squared plus y squared equals z squared, just the Pythagorean theorem. Okay? So moving on to step 2 from this, we say, all right, which of the 3 variables we have to consider here, x, y, and z, which of those vary with time and which remain constant? So, which remain constant here?
The ladder height.
Okay, I heard 2 completely conflicting things. What?
But the ladder height is constant.
Okay.
Z.
Okay, the ladder. Okay, yeah. So yeah, the ladder stays constant, so z. So z is constant. And so to see what that is, well, since z corresponds to the ladder, which is square root of 8 meters long, z will then correspond to the square root of 8 for every single moment that we're considering here. And then, of course, x and y are going to vary with time. Okay? So then that implies that, well, if z is always constant, then that means we can just plug that into our Pythagorean theorem to get that x squared plus y squared, in this case, just equals 8, because square root of 8 squared is just 8. Okay? So now, moving on to step 3 from this, we say, all right, let's take a look at what we're given, and what do we need to find? Okay, so let's see. So we've already used square root of 8, so that's not really, we don't really need to worry about that anymore. So then what we're also saying is that the foot of the ladder is then being pulled away from the wall at the rate of 0.7 meters per second. So what that says is that here's our ladder, and then we're basically taking the base of the ladder, or the foot of the ladder here, and then just pulling it away. Okay? And it's going to be going at the rate of 0.7 meters per second. So if that's the case, what would that 0.7 correspond to here? What quantity?
dx dt?
Exactly. Yeah, because in this case, the 0.7 is changing the x, so that means that this will correspond to dx dt. So 0.7. And we have to focus on how fast is the top sliding down the wall when the foot of the ladder is 2 meters away from the wall. So what would the 2 meters correspond to here? So when the foot is 2 meters away from the wall.
dx.
Just x, right? Equals 2. Okay. And then that gives it, that's all the given information we have. So now how fast is the top sliding down the wall? So what would that mean that we need to find?
dy dt.
Yep, dy dt. Okay. So that tells us everything we need to find. Or no, it tells us what we need to find and what we're given explicitly in the problem immediately. Okay, so now step 4. We have to differentiate this equation here with respect to time t. So as we had last time, treat x and y as differentiable functions of t. Okay? So then if that's the case, we have d over dt of x squared plus y squared equals d over dt of just 8. Okay? So then a slightly different way of stating this is just, well, d over dt of x squared plus d over dt of y squared equals d over dt of just 8. Okay, so then if we go ahead and carry out the differentiation with respect to time t, what does the equation become? Let's give someone else a chance.
Dx plus 2y dy equals, or I mean dt.
Yep, there,
Excuse me.
there you go.
Equals, and then 8.
Wait, what? So,
0.
yeah, there you go. So derivative of 8, which is always constant, so 0. Okay, and so the good news is that with these types of problems, there's always going to be a 2 here because of the fact that we're always going to have a square here, right? So the good news is that with problems like this, you can just get rid of the 2, so you can just focus on x times dx dt plus y times dy dt. So ultimately, you just get that. All right? So the good news is that, well, we have x and dx dt, and we need to find dy dt, but, oh, wait a minute, we don't have y, though. So how do we figure out what y is, though? Any thoughts or suggestions to figure out what y could be?
Well, since we know what x and z is, we can solve for y.
Exactly. So this is going to harken back to what we did in the first example from last time, in that we have to plug this back into the original equation here, or I guess in this case here, depends on how you want to look at it. So if you plug in x equals 2 back into this equation here, then that should be able to give you the y value at that time. So can get y from x equals 2. So if you plug in x equals 2 into x squared plus y squared equals 8, then we have 2 squared plus y squared equals 8. So then that should tell you, okay, so if you go ahead and carry everything out and solve for y, what should you end up with as the value here? And just 2, right? Because you just have 4 plus y squared equals 8. And carry out the remaining algebra to get that y is equal to 2. Okay? All right. So then now that we have all the needed values, step 5 is just, well, we have x, which is 2, and then dx dt, which is 0.7, and plus y, which is 2. And then dy dt, which equals 0. So then from this, you should be able to pretty quickly see that dy dt at this moment in time then becomes what? Yep, negative 0.7. Good. Meters, in this case, meters per second, because that's our units given in the problem. Okay, and that's example 1. So any questions on that? All right. Okay, so moving on to example 3. Oh, sorry, example 2. Sorry, I have page 3 and example 2, so that's going to throw me out for a bit. All right, so does anyone still need example 1 stuff? Okay. All right, so example 2, we have, in this case, a baseball diamond is a square 90 foot on one side, and a player runs from first base to second base at 13 feet per second. At what rate is the player's distance from home base increasing when he is halfway from first to second base? Okay? So in this case, let's go ahead and let x, y, and z be the following sides. So here we have, we focus on this right triangle here. So right triangle here. Then let's go ahead and denote this by x, this by y, and this by z. Okay? So let's go ahead and translate that over to here. Okay. Okay, so then z, y, x. Okay, so the good news is, again, we don't have to deal with any angles in this problem. So in this case, we could just go ahead and let our needed formula be the Pythagorean theorem again. All right, so nothing crazy with that part. But now step 2, let's go ahead and figure out which of the 3 variables are constant and which vary with time t. So which of the 3 would be constant here? And what would the corresponding value be? Go ahead.
Y, dy dt is y.
Well, so in this case, that if you look at the picture, we notice that the player is always running towards second base, right? So it seems like y is going to be varying with time t, and then consequently, if he's going to, and the player's going this direction, that means that the distance between him and home base should always be moving as well. So in this case, y and z should vary with t. But then what about x? That's always going to be constant, right? So in this case, x is always going to be constant, and in this case, well, the problem states that the baseball diamond is 90 foot on one side, so that means that this should always be 90. Constant. So consequently, we have, well, 90 squared plus y squared equals z squared. Okay, so now let's go ahead and move on to step 3 from this. So let's take a look at what we're given and what we need to find. So, like we said, we've already used 90, so that's not relevant in this within the context of step 3. So the player runs from first base to second base at 13 feet per second. So what would the 13 correspond to here?
Dy dt.
Right, dy dt equals 13. And this problem states that at what rate is the player's distance from home base increasing when he is halfway from first to second base? So if that's the case, at that particular moment in time, what should that tell you about, what could that tell you about one of the quantities that we need to be given here? Let's give someone else a chance. So we need is halfway from first to second base.
Y would be 45 because of half a 90.
Yep. Y equals 45 because, well, Y always corresponds to the distance between first base and the player, and if the player is moving to second base, that means that the halfway point would be the halfway point will be 45 because the side of the diamond is 90 feet. Okay? And so at this point, the problem asks us to then find the rate at which the player's distance from home base increases, so that would correspond to what rate? So it's already established, well, this corresponds to the distance, z corresponds to the distance between the player and home base, so in this case that would just give you that this rate here would be dz dt. Okay? So that's part 3. So let's go ahead and differentiate this equation here with respect to t, now that we have everything we need from the problem. So if we differentiate this equation with respect to t, well, similar work as parts or example 1 should then yield what?
Uh, 0 plus 2y dy dt equals 2z dz dt.
Right? Good. And because we always have a 2 here, we can just simplify this down to just y times dy dt equals z times dz dt. Okay? So now it looks like we're running into the same problem that we had before, because again we have y and dy dt, but even though we do need to find dz dt, we don't have z yet. So it looks like we're going to need to figure out, we need z, so it looks like we're going to need to plug this back into our equation here again to figure out what that value of z is. So we can get from, so in this case, if we're focusing on the particular value at y equals 45, well, like we had in the last problem, let's go ahead and plug that into our equation here to get z equals, well, the square root of 90 squared plus 45 squared. So if you add 90 squared and 45 squared, well, what you'll notice is that this is going to end up equaling, it's going to equal the following value. So what we'll do with this actually is this. So to make things a little bit easier in terms of simplification, what we're going to do is we're going to say, all right, 90 squared is the same thing as 2 times 45 squared plus 45 squared. So then this is the same thing as saying, all right, well, it's just 4 times 45 squared plus 45 squared. So what you'll notice here is that if we say, all right, if we factor out 45 squared from both terms here, then, and then throw it outside the square roots, then this whole expression would simplify to what? So we throw out 45 squared and then take it outside the square root.
45 squared square root 4.
Well, then, well, plus 1, right? Because we have, so 45, quantity squared, plus times 4 plus 1. So we have essentially just 45 times the square root of 5 here. Okay? So what that implies is that moving on to step 5, that tells us, okay, so we have y equals 45, dy dt equals 13, and then z, as we established, is 45 times root 5, and then dz dt is what we need to find. So then a quick little bit of division later should then tell you that dz dt is just 13 over the square root of 5 in this as the quantity, and then the units would be feet per second. Okay. So, any questions on example 2? Okay. Alright, so what we're going to do from this is say, alright, so example 3, so this one you can kind of tell I kind of stole this from last year because of the meme that resulted from that time period. So with example 3, the premise is an Area 51 raider sees a UFO flying away at a speed of 450 miles per hour at an altitude of 4 miles. So for the first part here, I'm just going to go ahead and say it's similar enough to what we've been doing up until this point to say, okay, I'm going to go ahead and skip this part. So see notes on webpage. So it's similar enough to what we've been doing to the point that I'm just going to go ahead and say skip it for now. So here, what we will do here is say, all right, let's go ahead and label our usual z, x, and y here, because we will need that for part 2. So with part 2, this one's actually a bit different, because now, if you look at the rate, we have to figure out the rate at which the angle of elevation decreases when the angle is pi over 6. So here, in this case, we actually do have to deal with an angle here. So in this case, since it's the angle of elevation, in this case we have to deal with this angle theta here as per the setup in the beginning of class. So as we established there, we have to be a bit careful. So with step 1, in this case we need to deal with one of the trig equations. So we need trig. So check what's given. Check what's given to see which one. Okay. So we need to figure out which of the 3 trig equations from SOHCAHTOA we need to figure out which of those 3 we need. Okay. But for now, let's go ahead and move on to step 2 to see what we need. So the premise is that the UFO is flying away at a horizontal speed of 450 miles per hour. So it's going 450 miles per hour in this direction. And it's going at an altitude of 4 miles. So in this case, this y here is always going to be 4. So, but otherwise, in this case, if the UFO is going in this direction, that means that x is always changing, and then consequently, so are z and theta. So in this case, the only thing that's constant is y, so y equals 4 here. Okay? So with part 3, let's take a look at what we're given. So in this case, as I already mentioned earlier, this 450 will change the horizontal distance with respect to the ground. So as I said, dx dt will be 450. And then we have to figure out we're focusing on the moment when the angle theta is pi over 6. So this is just pi over 6. But then we're saying, okay, we have to figure out at which the angle decreases. So in this case, that should pretty quickly tell you that we got to figure out d theta dt. Okay? So here's what happens with this. So of the 3 trig equations, that means we have to use the one that uses x because we're dealing with dx dt. We have to deal with y because we know what y is, and we also have to deal with theta. So which trig equation uses x, y, and theta. So of the three that we've established, which trig equation uses these three in particular? Tangent. So in this case, we have tangent of theta equals y over x, which in this case is just 4 over x because of the fact that y is always constant. So as a result, that means our equation ultimately becomes 4x to the negative first equals tangent of theta. Is our equation here. All right. So, moving on to step 4. If we differentiate this equation that we just established with respect to t, 4x to the negative first equals tangent of theta, then what is the resulting equation we end up with? Go ahead.
Negative 4x to the negative 2 dx dt.
Yep.
Secant squared.
Okay.
Squared.
Yeah. So this is the left-hand side. So then the right-hand side becomes secant squared of theta times
d theta dt.
d theta dt. Good. Okay. Okay. So that's good. So that takes care of the differentiation part. But that says, all right, so we have dx dt, we have theta, so we can get secant squared, and we're trying to find d theta dt. But oh wait a minute, again, we still need x here. So in this case, how do we get x here? Well, we still have this equation from before, so let's figure out what x is from that. So go ahead and write this in red. So you need x. So in this case, if we plug in theta equals pi over 6 into this equation here, we have tangent of pi over 6 equals 4 over x. So if you recall, what is tangent of pi over 6? Does anyone remember from the good old unit circle? Okay, seems like a lot of people have forgot, so I'll just go ahead and say for now, make sure to remember the unit circle, but for now, I'll just say that the tangent of pi over 6 is 1 over the square root of 3 equals 4 over x. So that should pretty quickly tell you that if you solve for x in this case, you should have x equals what? X equals what? Is what exact value? Go ahead.
4 squared root of 3.
4 squared root of 3. Good. Okay. So now let's go ahead and plug that into our equation. So we have negative 4 over, so we have 4 square root of 3 quantity squared times dx dt, which is 450, equals secant of pi over 6 quantity squared times d theta over dt. Okay. So what that tells us is that, all right, so let's go ahead and simplify this a bit. So on the left-hand side, we have negative 4 times 450 over, let's see, 4 root 3 quantity squared equals 16 times 3 And then on the right-hand side, we have secant of pi over 6 quantity squared. So does anyone remember what secant of pi over 6 is? Does anyone remember what cosine of pi over 6 is? Okay, so seems like some people forgot, so I'll just say in this case, secant of pi over 6, if you recall, is 2 over the square root of 3. So square that to get 4/3. So then times d theta dt. Okay. So then what you notice is that on both sides here we have a 4 and a 3 on top and bottom respectively. So what you can do is say, all right, if we multiply 3/4 to both sides here, then these cancel each other out. So ultimately you're just left with d theta dt equals negative 450 over 16. Okay? So that would be your answer here. Okay? So, and then of course, because we're trying to figure out the rate at which the elevation angle decreases, you would not include, so do not include the negative in ln kappa. Okay. So don't include that in ln kappa when you put that in, because we're trying to figure out the rate at which the angle decreases, so you don't need to worry about the negative putting that in here. Okay, so any questions on that? Alright. Alright, so now the last problem. The premise is that a fictional country starts bike races in the following way. So, a celebratory balloon initially hangs 50 meters in the air. Once the race starts, the balloon begins rising at a rate of 5 meters per second. Bicyclists then start the race under the balloon, traveling away in a straight line at a constant speed of 10 meters per second. And then the question asks, how fast is the distance between the bicyclists and the balloon 10 seconds later? Okay. So again, no angles here, so let's just have x, y, and z. So what the problem then asks is this. So once the race starts, and let's say that that's at t equals 0. At t equals 0, the balloon begins rising at a rate of 5 meters per second. So in this case, the balloon will be going up at 5 meters per second. So let's go ahead and cover this. And then once the race starts at time t equals 0, the bicyclists travel away in a straight line at a constant speed of 10 meters per second. So 10 meters per second is this what's going on there. And then we're trying to figure out how fast is the distance between the bicyclists and the balloon 10 seconds later. Alright? So step 1, like I said, no angles, so still use Pythagorean theorem. X squared plus y squared equals z squared. Step 2, well, in this case, we have x and y are still changing because of the respective velocities. And then z, well, consequently, will also change because of the fact that the balloon and bicyclists are going away from each other. So in this case, x, y, and z vary with t, so nothing crazy there. So 3, we say, all right, taking a look at what we're given. So from now, in terms of explicit values, the only ones we're explicitly given in terms of actual quantities we have are these two velocities here. So in this case, this x here, this 10 here, because that's increasing x, well, that should pretty quickly tell you that's dx dt. So that's 10. And then since this 5 meters per second increases y, that should tell you that 5 will correspond to dy dt. And then, of course, we're trying to figure out how fast is this distance here changing 10 seconds later. So we need to find dz dt equals that. Okay. So in this case, there's no constants here in this particular problem with respect to x, y, and z. So for now, let's go ahead and differentiate this as we've been doing. So similar work as the first two examples should pretty quickly tell you that this is just 2x times dx dt plus 2y dy dt equals 2z times dz dt. Okay. Or if you want, you can go ahead and cancel out these two factors to make things a bit easier. So we have x times dx dt plus y times dy dt equals z times dz dt. Okay. But now here's the catch. We don't have any of x, y, or z here. We have dx and dy dt, but now we need to use the remaining data to figure out what's going on. So in this case, we still need x, y, and z. So we need to use the data at 10 seconds later to figure out what's going on. So use 10 seconds later to get them. Now remember, x, y, and z are all still functions of time t. So in this case, we say, all right, so what we said that the race starts at time t equals 0, right? This as we've established back up here. So at x equals 0, if we treat this point here as 0, where the bicyclists start, this would be 0. And then y of 0, that means that the corresponds to the initial height, which in this case is 50. All right? Okay, so then let's take a look at how to get x of t and y of t from this. So let's take a look at x of t here. So to start off here, what we notice is that we're going always at a rate of 10 meters per second. So what that says is that, all right, if we have 1 second later pass, then the position is going to be 10 meters, but if 2 seconds pass, 20 meters occur, and then so on and so forth, right? So then what should that tell you about x of t in this case?
100.
Well, just focusing on x of t here.
10 times t.
10 times t, right? Okay. And then similarly, so in that case I would tell you that x of 10 is 100, as you established. But then, in a similar fashion, y of t would then be what? Actually, go ahead.
y of t plus 50?
So in this case, the y of t corresponds to the balloon here. So in this case, we have, all right, so if 1 second passes, then the balloon's going to be at 60, and then 2 seconds later at 55. So if 1 second passes, the balloon's going to be at height 55. 2 seconds pass, we're going to be at 60, and so on and so forth, right? So that should tell you that we have 50 plus what? 5t. Good. So then y of 10, consequently, will also be 100. Okay. So as a result, that should tell you that at time t equals 10, that should tell you that if we use these two values so this would mean this would be our x value and this would be our y value. So as a result, if we plug this into the Pythagorean theorem, then z should be what? What exact value? Yep. So we have 100 squared plus 100 squared equals 100 times square root of 2. So then, now that we have all of these, let's go ahead and plug them into step 5, which is, well, 100 times dx dt, which is 10, plus 100 times 5 dy dt, and that equals 100 times square root of 2 times dz dt. Okay, So then what you notice from this is that, well, the hundreds cancel each other out. This ultimately becomes 15 if you cancel out the hundreds. So then ultimately dz dt is then equal to 15 over the square root of 2. So if you simplify everything, you should get that as your final answer. Okay. Okay, so any questions on that? All right. Okay, so that's all I have for today. So I will see you guys on Monday. Have a good weekend.